Hi everybody. Can everybody see and hear me okay?
Yeah, we've got your screen and your webcam and your view perfectly. Oh,
Great. Okay,
yeah,
thank you, and thank you for the introduction. As we just mentioned, my name is Celeste Cunningham, and I'm doing my PhD at the University of Ottawa under the supervision of Bill Arnott. So the rocks I study belong to the Windermere Supergroup, which is a 6 to 9 kilometer thick succession of mostly marine rocks that were deposited on a passive margin during the breakup of Rodinia in the mid to late Neoproterozoic. My research group, again led by Bill Arnott, studies the deep marine slope deposits of this supergroup, and my specific PhD project is looking at levee deposits associated with slope channels. My fieldwork is conducted at the Castle Creek study site in BC, Canada, where levee deposits are vertically dipping and exceptionally well exposed due to glacial pollution, and this allows for detailed observations to be made at a wide range of scales. Samples taken from the field were examined using both optical petrography and electron microscopy, as well as various geochemical analyses. And to better understand the nature of OM-rich strata at Castle Creek, as well as its distribution, samples were taken for geochemical analyses every 5 to 10 meters along a vertical transect 300 meters long, with additional sampling of OM-rich beds. And this 300-meter transect was actually only part of a much bigger study conducted by a few other students in addition to myself, which included the sampling and geochemical analysis of 3 separate 2-kilometer thick vertical transects at the study site. So just to quickly refresh everyone on levees and their formation, flows that travel downslope within slope channels often spill out of the channel edges, as you can see in the top 2 diagrams, and in doing so they create these wedge-shaped sediment deposits called levees. In the top right, you'll also notice that much of the sediment that spills onto the levee is fine-grained suspended load, such as fine sand and mud, and that coil soil sediment, such as coil sand and gravel, often remains confined within the channel. Because of this, levee strata are typically dominated by thin to very thin bedded mud, mostly mud and fine sand. Levee strata also thin and fine away from the channel itself, which is shown in the cross-section of a channel levee system down at the bottom of the slide. So levees have also been found to contain significant amounts of organic matter. In modern systems, levees have been shown to sequester a significant proportion of the total annual global flux of organic carbon, with an estimated 10 to 20% alone in the modern Bendel fan, which is shown in the upper right. In some systems, such as the Brown-Powell field in the Gulf of Mexico, these organic accumulations have even been significant enough to form economic petroleum soil straps. Because levees are these extensive features that undergo high rates of sedimentation, they actually act as ideal sites for significant carbon accumulation and preservation, and that's why we've seen these accumulations both in ancient systems and in modern systems. 2 organic-rich facies have been recognized at the Castle Creek study site: organic-rich mudstone and organic-rich sandstone. The TOC in these facies can be as high as approximately 15% once they've been adjusted for the effects of greenschist metamorphism, which is estimated to have resulted in the loss of 50 to 80% of the original organic content. OM-rich mudstones, facies 1, are black and extremely fissile and consist mainly of clay grains with less amounts of silt. They also have an abundance of rhomboidal pyrite within them, as you can see scattered throughout the photo on the left. Sandstone beds with elevated TOC consist of alternated bands of black, mud-rich sandstone and orange, highly cemented sandstone. And because of this, I've informally named them tidal-striped beds because of their close resemblance to these big cats. And again, as you can see, these strata are visually quite distinct from typical slope sandstones and mudstones, which are light beige to light gray, respectively. And organic-rich sandstone is actually the more common of these 2 facies, and constitutes about 85% of the OM-rich strata at Castle Creek. Soft sediment deformation and lode structurals are also quite common in these bands. And interestingly, OM-rich sandstone beds are much thicker than typical levee beds and range in thickness from 30 to 140 centimeters thick. The organic carbon isotope values in these samples range from approximately -22, -22 to -26 per mil. And because this was a Neoproterozoic and terrestrial plants did not yet exist, the potential sources of this OM are limited to algae and phytoplankton. And this is consistent with the measured isotopic values. This organic matter would therefore be considered type 2. So the organic matter that we see can be grouped into 3 separate types, each of which is shown in one of these SEM photos. The first type is discrete silt to sand size carbon grains. The second is sand size organomineralic aggregates. And finally, we have nanometer to micrometer scale totems around clay grains. Types 1 and 2 are both interpreted to be detrital grains that were sourced from disaggregated bacterial mats that grew on the continental shelf before being remobilized downslope. However, these 2 types are relatively uncommon, and it's type 3, on the other hand, that's quite abundant, and this type constitutes approximately 96% of all of the OM available to Castle Creek. This type occurs as thin black totems around and in between clay mineral grains. So the clay grains in the black mud-rich sandstone bands that I showed before, as well as the clay grains that comprise the OM-rich mudstones. All of these are surrounded by these nanometer scale black rims related to adsorbed carbon-rich films on clays. And this final type is interpreted to have originated as freely suspended micro and nano-scale organic compounds, such as EPS, from the upper water column over the continental shelf. And these then became physically attached and or chemically adsorbed onto the surface of clay grains and subsequently were resedimented by suspension settling and active transport into the deep sea. Interestingly, these OM-rich beds don't stack directly on top of each other, and instead they are dispersed among typical, relatively OM-poor levee thin beds. And so this suggests that most of this OM was not delivered by the typical flows that deposit levee thin beds, but instead by extremely large sandy flows that were highly enriched in shelf-derived OM. The cause of these unusually big and organic-rich flows is something I'm currently looking into and hope to find out more about. But for those of you who attended on Wednesday, some of the work done by Peter Talon and his group might be quite relevant to this, and it could be these preconditioned slope conditions that then are triggered by events and form giant uncommon flows. It could be something like that, but it's definitely exciting. Additionally, within the 300-meter thick succession of mostly levee deposits that I sampled in this study, these OM-rich beds are only found in one stratigraphic interval throughout this succession, which suggests that the basin conditions at that time were, for one reason or another, conducive to the production, accumulation, and or preservation of OM. And you can see this is just a chart of the TOC, as well as an outcrop image with the lithostratigraphic unit shown. And you can see this huge spike all of a sudden about halfway up this interval where TOC just kicks off and then decreases again. And so to investigate this distribution, I used geochemical proxies to examine trends in sea level, primary productivity, redox conditions, plastic inputs, and weathering intensity throughout the whole succession. And each of these are shown in this diagram. The OM-rich interval itself is highlighted by a box with red dashed lines. And I know that there's a lot going on in this slide, so I'll try to walk you through some of the main observations and takeaways. During the interval of increased TOC, relative sea level was quite high, and high sea level has often been associated with high OM accumulation and preservation, so this seems to make sense. Additionally, at the base of this interval, there's a distinct spike in primary productivity proxies, which again makes sense. If you have a lot of production, you can obviously accumulate and preserve more of the sediment. However, notably, conditions were fully opposite throughout this whole succession, as is shown by the first 3 redox proxies, which indicates that ocean anoxia did not contribute to the preciptation of this OM, which is typically considered a requirement. However, the oxygen concentrations may have been slightly lower than average in this interval, which is indicated by the higher values in the 2 vanadium proxies and the lower manganese to iron ratios, and so this could still have aided with the preciptation. The base of this interval also corresponds to increased plastic input and weathering, which may have resulted in abundant nutrient input to the shelf and promoted this observed increase in primary productivity. So it seems like together, these factors combined within this one specific interval to create conditions that were extremely conducive to the accumulation and preciptation of OM. And finally, I would just like to briefly touch on why this OM is concentrated in the levees and not elsewhere in the system. And although primary productivity is highest on the shelf and not in the deep marine at all, the oxidation and respiration of OM remains in relative equilibrium with photosynthesis. And this maintains a balance between the consumption and the release of carbon dioxide and oxygen. However, when OM gets transported downslope by sediment gravity flows, much of it is adsorbed onto clay grains, as we've seen. And because of this, it's concentrated higher up in the flow and ultimately ends up overspill in the channel and getting deposited on the levees. These high sedimentation rates, particularly of fine-grained sediments, which limits diffusion, coupled with this additional protection by absorption, prevent its destruction by oxidation of respiration once it's been deposited, thereby effectively sequestering huge amounts of carbon in the sediment and acting as a net sink for atmospheric CO2. And significantly, as we've seen, this preciptation can occur without any special conditions, such as bottom water and oxidant events in the ocean. And so now just to summarize, these depositional processes in levees result in the concentration and enrichment of sedimentary marine or organic matter, which originated on the continental shelf before being transported downslope. OM was predominantly transported to the deep sea by anomalously large sediment gravity flows that continuously overspilled the levees and formed thick, sand-rich beds instead of the more typical mud-rich levee thin beds. Most of the OM found in levees is closely associated with the surfaces of clay mineral grains and is found in thick, banded, mud-rich sandstone beds. The factors which control the concentration of OM into that one stratigraphic interval include sea level, primary productivity, plastic input, and weathering intensity. And this study helps to elucidate the role of these different paleoenvironmental factors in deep marine organic matter enrichment, and they may be useful in the future to study organic carbon accumulation and preservation in both modern and ancient systems. Thank you.
Thank you very much, Celeste. Very important topic, potentially very important for the carbon cycle. So very interesting new route to take this field site to. While we wait for other questions coming in through the question box, my initial question will be if you can comment on what do you think produced this organic matter. If we focus on the material that's surrounding the clay particles, perhaps, because that's the most important component in your study. So what made this organic matter? What life should I think of?
So I think most of that would have been produced by free-floating algae and phytoplankton that would have been most abundant up in the shallow shelf. And a lot of what we actually see would have been the result of various organic compounds and polysaccharides produced by this marine floating algae that then chemically bonded with the clays and was transported downslope.
I see. So like biofilms and flocculation.
Yeah, exactly.
Okay. So another question about your methodology. Like I don't quite see how you justify multiplying the organic carbon content by 5 to get the the primary organic carbon content. It's a correction for the metamorphosis, but do we really think that the mobilization of carbon is so large? It doesn't seem in your petrographic images that that somehow it doesn't look like 80% of the carbon was mobilized and taken out. How sure can we be of that carbon loss in the metamorphosis?
So unfortunately, not too sure. We do it. It's more out of range. Again, studies that have evaluated how much OM is lost in the drops of the same level of greenschist have estimated between 50 to 80%. So I know in my slides I showed the potential maximum amount, but really we have to work within that range of it could be anywhere between twice as much and 5 times as much. But a lot of that is just the high heat, these drops of on and lower greenschist level. And so that has unfortunately damaged a lot of the carbon bonds and resulted in the loss of quite a bit. So even though we do see a lot of it in the rock still, and it might not seem like we've lost 80% of it, it is still possible that we've just missing most of what was once present. But
Okay.
it is inexact and within a range that we look at.
Yeah, well, impactful results regardless of that factor, I guess. Thank you very much. And